Sound is a physical event. Hearing a noise is actually experiencing a sequence of invisible atmospheric impacts violently striking the side of your skull. But the biological sensors required to decode these impacts are not exposed to the air. They are submerged deep inside the dense, fluid-filled labyrinth of the inner ear. This logic model illustrates a severe mechanical problem known as acoustic impedance mismatch. When wide, low-force airwaves strike a dense liquid boundary, the vast majority of the kinetic energy simply reflects right back. Left unresolved, 99.9% of incoming acoustic energy would fail to breach the inner ear. The organism would be effectively deaf to the surrounding environment. To capture this energy, the anatomy must execute a physical conversion. It has to take wide, low-pressure atmospheric ripples and compress them into a highly concentrated, high-pressure physical strike. The outer structures of the ear exist to solve this exact physics problem. They act as a dedicated mechanical adapter, bridging the properties of air and fluid. The process begins at the tympanic membrane. This biological drumhead completely seals the internal acoustic hardware from the outside atmosphere. Its specific function is to flex inward and outward, vibrating perfectly in sync with rapid fluctuations in air pressure. To do this, the membrane operates under a strict structural paradox. It has to be incredibly thin to detect microfluctuations in pressure, yet resilient enough to avoid rupturing under heavy kinetic loads. Once the air strikes this surface, the kinetic energy is successfully trapped inside the biological system, manifesting as a wide, low-force physical vibration on the drum. Capturing the vibration achieves the first step, but this energy remains far too weak to physically push the dense fluid of the inner ear. This is where the ossicles take over. These are the malleus, the incus, and the stapes, the three smallest bones in the human body, physically linked to the interior surface of the tympanic membrane. Functioning as a rigid, interlocking lever system, these bones catch the wide vibration from the tympanic membrane. They funnel it to the microscopic footprint of the stapes, shrinking the force area to increase kinetic pressure by a factor of 20. The final action of this bone chain is a highly concentrated, violently powerful piston strike against a small opening called the oval window. This 20-to-1 mechanical compression overcomes the impedance mismatch, generating enough pressure to punch atmospheric kinetic energy directly into a fluid environment. That fluid environment is the cochlea, a dense, bony cavern shaped like a coiled snail shell. This is the primary acoustic processing chamber. Here, the raw physical force delivered by the middle ear will be prepped for data extraction. When the ossicular piston strikes the oval window, it physically displaces the liquid inside the chamber. This action generates a massive, rapid hydraulic wave that propagates deep into the oceanic fluid of the cochlea. However, because the cochlea is encased in rigid bone, the fluid inside is completely incompressible. It has nowhere to go. To allow the fluid to move, a secondary relief window at the far end of the duct bulges outward as the piston pushes inward, permitting a closed-loop pressure wave to travel freely. The kinetic strike has successfully become a hydraulic wave. But raw fluid motion is useless without a mechanism to decode the specific frequencies hidden within. That decoding relies on the basilar membrane, a long, flexible geometric ribbon suspended lengthwise through the center of the cochlear fluid. This vector schematic highlights how the ribbon acts as the biological hardware's physical frequency analyzer. As the hydraulic wave surges through the cochlea, the surrounding fluid dynamics force the basilar membrane to ripple perfectly in sync. But the membrane does not respond uniformly to the wave. Its structural properties vary drastically from one end to the other. This precise, graded stiffness is the mechanical prerequisite for deconstructing a complex sound wave. At the membrane's base, nearest the piston strike, the ribbon is extremely narrow and structurally stiff. This high-stiffness region is built specifically to catch and resonate with rapid, high-frequency kinetic waves. Conversely, at the apex, deepest in the spiral, the membrane is significantly wider and floppier. This low-stiffness region resonates exclusively with slow, low-frequency hydraulic waves. This frequency map illustrates tonotopy. It is the physical sorting of frequencies based purely on where they cause maximum mechanical resonance along the ribbon. This sorting requires no digital or chemical computation. The physical geometry of the ribbon itself executes a mechanical Fourier transform in real time. By physically separating a complex cord into isolated spatial zones, the membrane perfectly prepares the incoming energy for localized data extraction. To see how that extraction occurs, we have to scale down to the microscopic surface of the resonating basilar membrane. Here you find stereocilia. These are microscopic biological pillars arranged in tightly clustered, rigid rows on top of the membrane. These pillars function as extreme sensitivity mechanical tripwires, suspended directly between the heaving floor of the membrane below and a rigid cellular ceiling above them. When a specific zone of the basilar membrane hits its resonant peak, the floor heaves upward. This action forces the stereocilia upward in perfect unison with the membrane. The massive hydraulic wave traveling through the inner ear has now been isolated into a microscopic upward thrust on a specific cluster of cellular pillars. As the membrane heaves, it smashes the stereocilia tips against the rigid ceiling structure above them. Trapped between the rising floor and the stationary ceiling, the pillars are forced to bend sharply to the side. At this scale, a microscopic tension line, the tip link, physically connects the top of a shorter pillar to the side of a taller one. As the pillars are forced to bend over, this link is violently yanked taut. Mechanotransduction bypasses slow chemical signaling pathways entirely. It relies purely on this direct physical tension. The taut tip link acts exactly as a literal tripwire, physically pulling open a microscopic trapdoor on the taller pillar. Potassium ions instantly rush into the open hatch, radically altering the internal voltage of the cell. The electrical threshold is crossed, firing a massive, instantaneous action potential. The kinetic punch of air is successfully converted into a raw electrical one.